You excited?
It's my first ever, so not really. Well, okay, listen. It's only like 15 minutes. It's not even interesting. And it's orthodontic, so I'm kind of looking at it as like my bio interview for everything else.
Yeah.
It's not my main goal, you know. So
It's good experience, but not.
yeah.
Yeah.
I'm not like dying on this hill that it has to go perfect.
All right. So, Taylor, good question about coupling constants. I'd forgotten about this. I was not taught about coupling constants when I first learned NMR, and so I kind of forget it's a thing until this lab comes up. So basically, we've talked about splitting and how that works because it's the pink, in this case, the pink protons interfering with the energy levels of the two blue protons. That type of interfering is called coupling. And what we can tell is because these two protons have different energies, the way that they interfere with each other is going to be consistent between the two signals. So the signal for the blue protons looks like a quartet, and it's going to be more de-shielded because of the halogen here. But both of them are going to have the same distance between the peaks within the signal. Right, so that's what we call the coupling constant is basically just that. What is the distance between these? Where it gets a little bit tricky is that the different measuring that is going to be different depending on what NMR you're using. The NMR instrument itself is going to operate at different frequencies. Higher the frequency, the better the resolution. What that does, though, is it means that in order to get a universal coupling constant that will apply in any NMR, we have to take the difference in ppm. So let's say that that's a difference of 2.57 to 2.54. We get 0.003. 0.03 ppm.
Which two are we?
I'm just making these numbers up. Just like the way you do it is you literally measure the difference between these two peaks, and then you're going to multiply by the frequency of the NMR, which you didn't have on the spectra that I gave you. So what you can do for the spectra I gave you is you can literally just look at this, measure it in centimeters if you want it, and just use that because what's going to be the same between both of these is this distance, 0.03 and 0.03. That's one of the ways you know what signal is causing the splitting. Because you can say, okay, well, these two both have differences of 0.03, therefore they must be the ones that are. Yes, exactly. So you can look. So you can.
Number two, I was like, okay.
So what is if you do 267? Do you subtract those two numbers?
What was that? Like this one and this one. I don't know why this is first.
So this is looking at that peak to that peak. It's giving you the difference between them. So if you just do the subtraction. So that's going to be a difference of like 80 ppm on this one, right?
So you run into these two.
You look at the difference between these two and compare it to those two. And if those are the two that are interfering with each other, it should be the same distance.
First one is 8.
Okay. And just looking at the numbers, the second one's really close to 8 as well, right? And that's going to be in ppm. Or actually, no, they already converted it for you. That's why you didn't even know what the frequency was.
Oh, see, I didn't know it was for.
Yeah.
Say that.
So that will mean you're coupling constant between these three.
So these are already inferred.
Right. And I didn't catch that when I looked at it either. I was until I started realizing the numbers top didn't match PPM numbers on bottom.
Okay, so then what, that's if that's the whole number. What if you didn't have it already converted, you can get your difference in PPM?
You get your difference in PPM and then you multiply by whatever the NMR frequency is, which I would need to go back to the paper that's got the spectra from and figure and look at their methodology to see what they were using. There's something like 300 for proton NMR, 300 megahertz is pretty common. But if these are PPM, that's parts per million, right? And mega as a prefix means 10 to the 6, which is also a million. So if you're in PPM, you just multiply by the megahertz, and that gives you the J value in hertz.
So you multiply it, it's like, so it's.
So if you say, okay, for 1 ppm is 1 megahertz, basically, is that what it looks like a conversion is 300 megahertz if we measured this in at 300 megahertz. So 0.03 times 300 is going to give you something like 9, right?
Yeah, it's.
And so that allows us to say, okay, the interaction between these protons has a coupling constant of 9 hertz. So it's basically with the 2D NMR, it works the exact same way. Like if you're looking at the proton NMR or the carbon NMR, we don't see splitting in carbon NMR, so that doesn't apply. But you can say, okay, well, my splitting looks like this with a couple with this coupling constant. Therefore, I know these two must be the two that are causing the splitting.
And where did you get the dependent number from?
Just because I happen to know it's a relatively common number for proton NMR. Generally, your J value is going to be somewhere, if once you're in hertz, it's going to be somewhere between about 2 and 20.
So like, what would the formula of this?
Just ppm times megahertz.
But what if like you use like a frequency, what, just PPM?
So megahertz, yeah, ppm times frequency in megahertz.
Which is capital MHC. Capital M, capital H, lowercase.
Correct. All right, so why is this useful? Well, I'm just going to go over since we haven't really touched on this.
We need to know this.
No. But the difference in J values is also what causes some of that complex splitting, where you get a quartet of triplets versus a triplet of quartets. And here's a good example. Complex splitting can happen anytime we've got two different sets of protons causing splitting. So for the blue signal here, it has 5 nearest neighbors. So if they were all the same energy, we would expect that to turn into a sextet. But if they're, because we have this X value here, the coupling between B and C is not the same as between A and B. Because these protons have very different energy. So if we have a NMR that has a high enough resolution, if we don't have a super high resolution, then it will just look like a sextet, gets a peak of 6 splitting. If we have a high enough resolution, though, we'll actually see it turn into a quartet of triplets or a triplet of quartets, because if we ignore the green ones, there's coupling between A and B that's going to give us a quartet, because that's 3 nearest neighbors. But if we ignore the red ones and just look at B and C, that would give us a triplet. And so because those are two different energies, they have two different coupling constants, and so two things are possible. If your coupling constant between A and B is greater than B and C, then you wind up with your quartet being more spread out, and each line of your quartet turns into a triplet. On the other hand, if it's backwards, if the splitting between B and C is bigger than A and B, then you're going to wind up with a triplet having these be furthest apart. And then each line from the triplet is going to be split into a quartet. Right, and so remember that bigger difference in energy is going to cause bigger coupling constants. So I would expect B and C to have a bigger coupling constant. Just because there's a bigger difference in the energy values between these. So B and C, I would expect to see something that looked like a triplet of quartets. Right, and this also allows us to tell more about things like, okay, well, I basically kind of hand waved earlier and said, well, if you've got alkenes, that really throws everything off of your splitting, so don't pay too much attention to the splitting. It does allow us to say, okay, well, our splitting between across an alkene bonds, if they're trans versus if they're cis, that actually can tell us the stereochemistry. Because if they're vanillic trans, you get something in the 11 to 18 hertz range, versus if they're vanillic cis, you get something between 6 and 6. Now, obviously, that's not perfect because there's overlap. But it definitely could be a way that you can tell the substitution. And the same if they're on the same carbon, but you have two different things attached here. Let's say we had a C2H3 or H5 versus CH3, so a methyl versus an ethyl. These two hydrogens aren't identical now, right? Because one of them is cis to the ethyl, and the other one is trans to the ethyl. But they're not necessarily going to have any splitting because there's no nearest neighbors on this one. So actually seeing these two different peaks, they'll actually cause splitting with each other. And we'll see something with the coupling in the 0 to 5 hertz range. Right, so the fact that we can look at these different J values, and regardless of what instrument we're measuring on, they should have similar coupling constants like this. And we can do the same thing also if you're careful in the aromatic region. Ortho versus meta are going to have different coupling constants. So it's part of what turns our aromatic region into a big mess of signals is the fact that even the different substitutions are going to be slightly different in coupling with each other. So we can still trust the integration, and if you get good at this, then you can use those J values to really dig in and figure out the exact substitution on a benzene ring. But it's really kind of a more advanced topic and beyond what the way I usually approach these. Like I said, I forgot it was in that lab, but it was a good reminder to go back and cover this now that we've talked about NMR extensively. And when it comes to the final exam, you need to know none of that. I also remember being very confused the first time when I got to grad school, and that was one of the few topics that I was not prepared for when I got to grad school, and everybody else feel like, oh, it's a coupling constant. What do you mean you don't know what a coupling constant is? All right, let's talk about a few new types of reactions. Still in alpha carbon land. So this one's called the malonic ester synthesis. The malonic ester, it has this general form. Before we expose it to a strong base, we have this beta diester. which means we have a proton here that's really easily pulled off by a base. So what that's going to do is that gives us our phenolate, our doubly stabilized phenolate. So we have an extra resonance, which makes it a pretty strong nucleophile. So this is basically a more specific version of that alpha carbon halogenation we talked about on Tuesday. Right, because the alpha carbon halogenation was, okay, if you've got an alpha carbon, turn it into an enolate, use it as a nucleophile to do an SN2. This is just a really convenient way to do it because malonic ester is really easy to work with. And it's really easy to deprotonate that alpha carbon. Right, so this is also kind of a good review of what we did on Tuesday. And because, and I mentioned this the other day, if we wind up with two acid groups that are beta relative to each other, it's pretty easy to remove one of those by just heating it up. Remember, we called that step decarboxylation. When you heat something that has an acid group, if there's any sort of resonance stabilization, it's pretty easy to remove that acid group. And having it, this is not the only way that this works. Decarboxylation is also something that occurs a lot in plant products. It's one of the reasons that spices can lose their flavor over time is if they're exposed to heat over time, you can basically kick off a CO2 group, and that's going to change the way it tastes. Or in some cases, make a molecule biologically active. So, for instance, one of the most famous examples of this is in THC. THC is not psychologically active until you decarboxylate. So you can actually, a person could eat a pound of cannabis and feel nothing. But if you take a little bit of that cannabis and you heat it up above a certain threshold, it decarboxylates it and now becomes biologically active. And so it's a pretty common reaction to see happen. It's one of the reaction ways that we generate CO2 in our bodies is we decarboxylate the side products of glycolysis in the Krebs cycle. All right, so what is that decarboxylation step though? In this case specifically, what's providing the extra resonance stabilization is that other acid group. And that second acid group basically just gives us a way to stabilize this whole process. If you have two acid groups lined up like this, where the hydrogen from one acid group transfers to the oxygen on the other, we wind up with a relatively stable intermediate. They're not actually even showing here. If we just looked at it like this, so we just transferred over a hydrogen, one acid group to the other acid group, which we wouldn't expect this to necessarily be as stable because we have multiple charges on it, but it also means there's a pretty easy way for this rearrangement to happen. Right, so they actually broke it down. They didn't show the proton transfer as a separate step. But once you do that, you basically break this carbon-carbon bond to make a CO2 molecule. And get this sort of like a dienol. It's an enol that has an extra OH attached to it, which we know can tautomerize. We know that enols can turn into a ketone pretty easily, right? So it's just going to naturally do our normal tautomerization step, which will look like this basically. We show it in 2 proton transfer steps usually. You remember doing that?
Did we ever say that we were doing for our midterm for? I mean, there's challenges.
What do we want to do with it?
I was gonna like, but I even like was that thing or like.
Oh, that one. You did mean midterm. I thought you misspoke and we're talking about final. I did not see that email. What did you decide?
To do the points.
Do the points one, correct it and turn it back in? Okay, you're gonna do that too? Then let's just say, have you been working on it yet? Okay, let's say by Tuesday then, do that for your quiz this weekend.
Okay. And our research thing you want to say?
Yep. Gotta do it sooner rather than later, or else it stacks up into the final studying.
Yeah.
So the way that I would approach that if I had 2 deadlines for the same class is, when I'm taking a break from working on my poster, I'm correcting the test, because correcting the test should go faster and have a lot less brain energy to it. So you can do that kind of while you're recovering from working on your poster. Or your presentation, I should say. All right, so how do we use this malonic ester synthesis? We're trying to make this molecule. We look at what's attached to the alpha carbon here. Say, okay, well, that means I either need to start with one of these 2 green molecules, but with 2 CO2H attached, or you start with the diethylmalonate, because that's the one that's going to have, it looks like this. This is our alpha carbon that we can deprotonate. We can do it twice in a row. So we can start by using ethoxide to pull off the hydrogen and expose it to a benzylic chloride or bromide, whatever we want. Anything that's a good halogen, it's a leaving group in the spot where we want it. That's going to allow us to attach that carbon right here. So after we do it once, we'll get our same malonic ester, except now we also have this attached to the alpha carbon. There's still another hydrogen on that alpha carbon though, which means we can do it again. So then we can say, okay, well, step 3, NaOET again. And we need the other green molecule. So as long as we can get these two molecules, we can link them together. Basically, it gives us a way to link together any halogen or halides we want to a single carbon.
So.
Carl's getting pizza for the research projects.
So you're saying that gives us that, yeah.
Yeah. And so as long as we can get these two molecules, and we know we can make, if we just have polyamine, we know we can put a bromine on the benzoic carbon pretty easily, right, by using NBS and light. And depending on what we have in our stockroom, it might be harder to get this, harder to make this in the first place. So there's probably a way to do it. So this is just one more good way we have of linking these carbons together in a way that's pretty easy, that doesn't even involve us using LDA. Because remember, LDA does irreversibly create an enolate, but it's a really strong base. It's not particularly pleasant to work with. Whereas sodium methoxide is also a strong base, but it's pretty easy. Probably have some in the stockroom. And so this is what the first step would look like if we just did the first step. Oh, sorry, no, this is an alternative to using malonic ester. It's ethyl acetoacid. Ethyl acetate would just be this piece, and then you added another acetate group, acetyl group to it, acetoacetate. This is basically just another way of doing the same exact thing we did, except it's going to, because it's still going to work by deprotonating this doubly stabilized alpha carbon, and then using it as a nucleophile. But instead of getting a carboxylic acid attached, we get a ketone attached. And so to compare and contrast, here's our malonic ester synthesis. Diethyl malonate is going to lead to something that has a carboxylic acid attached versus acetoester is going to leave us with basically an acetone molecule attached. Which then has its own benefits because we know that working with ketone, there's a lot of stuff we can do to either remove that oxygen or convert it to a different functional group. All right, so let's do some practice. The top three, you can all use the malonic ester synthesis for. I'll draw the structure of the malonic ester. Versus the acetoacetic ester, which is going to look like
And then start with them on the fence without even make.
The top three, you can use the Melania to make because they're ending with an acid group still attached. The bottom three, because they're ending with a ketone attached, you're gonna use the acetoacetic ester.
And that attaches.
That's gonna attach to the alpha carbon in the middle, and then the last two steps are expose it to H3O plus and heat. And that kicks off that second acid group. Sorry, it converts both of the esters into acids and then kicks off the group as the CO2.
Oh, I was trying.
So if there's two things attached to the alpha carbon, we just have to do the first two steps twice. Give that a try and then I'll write them up on the board.
Does it matter which one we do first? Like,
You might want to do the bigger one first just because it's sterics. But shouldn't really matter. I should probably switch that. Probably the bigger one second because of sterics.
Why did you give us that?
Because methyl iodide is, it's either a liquid or a solid at room temperature, chloromethane is not. And I don't think bromomethane is either, so it's really common to use iodine. It's either ethyl or methyl. Anything larger than that, you'd probably use bromine or chlorine. I would mark you down though, if you said methyl bromide instead, that would work too. It's just less easy to work with. Then we do step 3. Another round of NaOET. Or just keep it basic. Then we're exposed to our phenyl chloromethane or bromo. Last step, H3O plus and heat.
Well, can you draw it before step 5?
Yeah. So before step 5, I'm just going to add it onto this one here.
You just add it to the same one.
To the same alpha carbon, yeah. And then after step 5, takes these ETs and converts them to a hydrogen, or like it turns the ethoxides into OHs. And then the heat drives off one of those acid groups. C is a little bit simpler because it's the same R group added twice. So we can kind of do that at the same time. We can say 2 equivalents of sodium ethoxide and 2 the bromopropane. And followed up with H3O plus and E. Should we take our break now and come back and practice the bottom 2 when we get back? Cement it in there a little bit rather than doing it before break and not thinking about it for a while. All right, let's say come back at, I'm not using this clock. I'm using a real clock. Say come back at 11.
Smell where. Yeah. Yeah. Okay, now. All right, thank you. Yep. So I brought my change proposal, and I have practice today, we're condensed the level fours and level threes for the last four practices. Because on Friday last week, I was the only one there. And, well, that's not true, I was there too, but I had much together idea. And, you know, and so it's not very good. So it's just like kind of really pointless, you know, it's just me doing things that they were telling me to do. That's. Regular practice. Yeah, but it's. So I think. Excuse me. We have like. But it's not. It is the only difference is. Starting with this instead of this. But then how do you get rid of? Their limits. So. But two. And that one. And then step. Page 3 on this. Probably just said. Yeah.
So what do we want to do about final suite? Do we want to wait until next week to figure that out?
Let's wait until next week, see where we are.
Okay. All right, let's work on these bottom two. So a reminder that acetic ester is going to look like very similar to the malonic ester. So this is ketone on that side. Good question. Seems like a physics thing.
I wasn't here.
Apparently you missed something good.
I know, she was supposed to record this.
What was it?
I
Here.
Oh, that's so weird.
You get yelled at. Mm-hmm. All right. So what are we looking at here? What's the alpha carbon and what's attached to it? So we leave this whole piece is going to be left over from this process. So we're just adding cyclohexyl chloromethane. So step one would be NaOET. Step two would be our alkyl halide. Step three, H3O plus and heat. This one's going to look really similar, except we have to do it twice. NaOET.
Sorry.
Yes, for the ethyl one, exactly. Not something I would mark you down on, but that's going to be more common. Speaking of practical considerations, why do we have to use NaOET? That's what's going to deprotonate, but could we use any strong base, or does it have to be?
Exactly, but it's easier to use. No, we can't. We have to use it because it has the OET, and then that's the same as what we're kicking off. I mean, it's be the same, but we're gonna have side reactions.
Bingo. In theory, this doesn't have to be ethyl ester. It could be something else. Ethyl ester is really common because it keeps the molecular weight high enough that it's going to be easy to work with. It's solid at room temperature. And everybody has it in their stockroom.
Right.
But you can use methoxy. You probably don't want to use just the acid. It needs to be an ester so that you don't get the carboxylation happening too early. But for these alpha carbon reactions that involve an ester, we're always going to want to use the base that's the same as our leaving group. So NaOET. NaOET again. I actually, my guess is doing the smaller one first would give us a better yield or faster reaction, but I don't actually know that. If I would actually want to go look something up or test it in the lab for a specific reaction. If I was going to be doing the same reaction multiple times. So I was getting picky about that. And then it's just an ethyl group, right? So ETI. H3O plus and heat. All right, so very, very focused, these two, but they're basically the same reaction that we worked on, the halogenation, or the alkylation that we worked on Tuesday. Just really practical way to do it. All right, So these are gonna be the trickiest ones. The last couple reactions we have are gonna involve an aldol condensation that then rearranges maybe the alpha beta unsaturated carbonyl. We talked about that happening before, right? If we have we do an aldol condensation and wind up with something that looks like this, for instance. If we heat that, we can get it to go through an elimination reaction. To make the alpha beta unsaturated carbonyl. Once we have an alpha beta unsaturated carbonyl, this is a really interesting reactive group because there's actually two spots that have partial positive as the resonance structure. So we have two spots where we can do an electrophilic addition. And so if we did a nucleophilic addition on this first resonance structure, it would just look like a regular nucleophilic addition that we learned back when we did carbonyls. Where you add probably a hydrogen to the oxygen side and any other nucleophile to the carbonyl carbon. But the fact that we also have a resonance structure that puts a positive charge on the beta carbon means we can actually attack with the nucleophile at the beta position as well.
Is this still one of our like elements?
It's still considered it's still part of this chapter because we get there by doing an aldol condensation, just like aldol condensation last week. Right, so we can control, we have two spots where a nucleophile can attack. That means we need some way to control which of those two spots our nucleophile adds to.
Right.
And generally speaking, the reactivity of the nucleophile is going to do it. Stronger nucleophiles are going to favor the 1,2 addition, where you attach it to the carbonyl carbon. A more stable nucleophile or a less reactive nucleophile is going to add a 4 position on the beta carbon. So it's either going to be adding on the active carbon, the carbonyl carbon, or the beta carbon.
So the less reactive is which one, the alpha or the beta, you said?
The less reactive nucleophile is going to have the beta position. And then we don't have a Greek letter for the alpha, or sorry, for the active carbon. A lot of times what you'll see for active carbon, it would just be an asterisk.
Okay. So then, and then the more reactive adds in the active carbon.
Correct. Right, so Grignard reagents are really reactive. But remember, the Gilman reagents are the ones that, if we wanted to do a single step, but not both steps on a Grignard reaction, we use the Gilman reagent. So if we do the R group attached to copper and lithium, we can add it in the beta position. If we use a Grignard reagent, we can add a carbon to the active carbon. Right, so we can also apply this to our hydrides as well. if we wanted to reduce it with, we use lithium aluminum hydride. That's definitely gonna add a hydride here. If we use the less reactive version, the lithium trialkoxy RO3 ALH. Remember that was the one that we used to just add a single hydride. If we use that version, we can add the hydrogen in the beta position. Yeah, I don't have any practice problems for that here, but let me pull up the textbook and let's get a practice problem for that. I guess we do have some. All right. Not yet. We're gonna add this other variable to it. It's just like we added melanic ester synthesis and acetoacetate synthesis. Or we're just specialized cases of that halogenation. Or that alpha carbon as a nucleophile. If we make an aldol condensation, this is actually going to tie two different topics from this chapter together. If we have that alpha beta unsaturated carbonyl, that is going to be a target for a nucleophile. If we use a doubly stabilized enolate as the nucleophile, it can come in and attack one of these two carbons, the beta carbon or the active carbon. But it's not a super reactive molecule or a super reactive nucleophile. So it typically adds in the beta position. And so this is called a Michael reaction. And I'm not sure why they changed the language on this from nucleophile to have Michael donor and Michael acceptor, but they did. The Michael donor is just going to be our nucleophile. It's just a very specific nucleophile that's a doubly stabilized enolate. And our Michael acceptor is going to be the nucleophile target. Right? And specifically the beta carbon. Right, so for it to be the Michael reaction, it has to be an aldol reacting with a doubly stabilized enolate.
You said it'll partially add to the beta chain?
Yes. So this is the one that's shown right above. So you can see this is the product that we're going to get. This is the beta carbon. We can label our alpha and beta carbons.
And you said the mic don't really let them stabilize. Your fire?
So the doubly stabilized anyway. It's so for it to be a Michael reaction, you have to have a beta dicarbonyl. And you have to have this, what do we call it, alpha beta unsaturated carbonyl. So now we're in practice. So if we treat each of these with the ethyl Gilman reagent,
Well, we wrote about it.
we see, I think it's usually the way it's written, sometimes LICU and then the R curves, but either way. That's gonna add to the beta carbon.
We need to do KOH first.
Yes, because the first thing we need to do is deprotonate. Actually, not for this one. Yes, over here.
Is that fine? I think we started. But if we know what the heat state is that
So that's our Gilman reagents. It's gonna act like a Grignard reagent, but only add to the beta part. It's less reactive. If we had this molecule plus a Grignard reagent, let's say we had ethyl magnesium bromide. That ethyl group would come in here and add there. If we're using a Gilman reagent, it's not as reactive, so it goes to the beta carbon instead.
what did you know?
So it would just be ETR, CULI. And then second step, H3O plus. Basically what's described in the problem. Can't really read that well. Identify the major product form following compound is treated with ethyl cupric lithium.
Yes.
It gets rid of the double bonds.
followed by non-SO. For the arrow would be the same as for.
For BS. It is, this is a cyanide group, or a nitrile group, instead of looking like a carbonyl, but it's still gonna serve the same function, being electronegative and pi bonds. So how do you feel about those? It's a little bit weird.
Yeah.
We're moving all the way over to the beta carbon, but at the same time, nothing we haven't seen before. I walked by and Kathy was using Swiffer yesterday.
Oh, sure.
She was.
So only.
All right, so what are we gonna see after step one here?
Outside carbon doesn't.
Correct. Drawing the mechanism would look like this. So after step one, we get the enolate. Which is going to come in here. And remember, we have two partial positives here that it can attack. For this one, it's going to attack the active carbon or the beta carbon.
I mean, it's based on how we have to.
Right. And the enolates are not considered especially reactive, especially the doubly stabilized ones. Less reactive means beta carbon.
Yeah.
So on the beta carbon, we add this whole thing. Should then color coding. There's our new bond. No, yeah, that's our new bond. What's the last step? Which is gonna do what? Especially considering that's not actually positive, is it? That was electrons over, right? So because this is an addition reaction, but because it's a nucleophilic addition reaction, we don't get a carbocation, we get a carbanion. So we're just gonna end up with a quick proton transfer at the end.
And that was.
That's a negative, yeah. So our final product looks like that. So these are microacceptors, aka the targets for our nucleophile. They're all fairly common with their beta carbons listed as being partially positive. And these are really common Michael donors. You'll notice that the nitriles are in there because they still act as a carbonyl in terms of alpha carbon chemistry. All right. You know what we're gonna do? We have one reaction left. 6 slides left. But I don't want to cover this next one today. Not ready. I'm not ready for it to be over. So you can work on your project. We'll cover it in class on Tuesday. And this weekend, do your corrections for your midterm. I'll make an assignment to submit that. Would it be helpful if I made that deadline earlier so it's not the same day? Would that get you done?
Well, we have something over on Saturday, we'll get to it for Friday or Monday. So-
Okay. So we'll just make it on Tuesday then.
Yeah. Oh, and it's Taylor's birthday on Saturday.
Happy birthday, 22.
I have items. What are we doing?